Hi guys. Today we will learn about the effect of RX ratio on power system. Furthermore, when you go, for more lecture, we will learn about the calculation part for the fault current. So that's why we need to learn about the RX's ratio. What's effect on the power system? Okay. Let's move on. I will show you. So first of all, RX ratio, it's a look at that. For example, I will draw first the R JX, and this is load. I will draw on the general operation situation on the power system. So what I meant is, so RX is jet impedance, right? R plus JX, right? So what I mean is, for example, if the fault, something in the circuit, something wrong in the circuit wrong, we will say fault current happened. So the most good example is, no, not good example. The most common example is a short current because that is the common part happened, and that is the biggest values. You know what I mean? So if the current happened, look at that. So the short current IS is happened in the circuit, this part. But as you know, in the cable, the jet is really low. So if we see the Ohm's law jet, right, in the cables, impedance is really low. So which means we have this voltage system, right? It's constant, which means this impedance is really low. So which means I is really big. That is, we say fault current happened. But what I want to say is I will focus on today RX ratio, right? So RX, so if as we know, here's triangle, RX jet triangle, right? So jet's magnitude is R 22 plus X 22, root is jet, right? So we will compare about, jet magnitude is the same. I want to say is, but the ratio is different, So what happened? We will compare. Okay. So what I mean is, the RX, ratio is more bigger. It's making more asymmetric waveforms. If RX is ratio is smaller, it makes a smaller asymmetric waveform. Let's move on. So here, you guys can see this black waves, as you guys, okay. I have, okay. Sorry guys, a little bit. Okay. Yeah, guys, look at that. This, the impedance is the same, okay? Impedance, I will say this is A, and this red waveform is, I will say, B, okay? The impedance magnitude is the same, but only difference is this ratio, okay? So look at that. RX's ratio is bigger than A's ratio is bigger than B, right? So look at that, the black waveform. This is, we say DC opposite, right? This line. And this is also DC opposite, this red line, right? But DC opposite is, look at that here. So the tau, this opposite is RL, right? RL is tau, right? But look at that. L is X, right? Here, look at see. I already explained about this equation, right? So what does that mean? R omega L is, X, right? So, which means, same meaning. Rx also means, tau. Tau is this DC opposite, right? So, which means, how fast, it disappeared, this, DC opposite. It happened because of the inductor's inertia, right? But the ratio, the Rx ratio, it makes it how fast it disappear or not. So what I'm saying is, look at that. So A, A waveform is, the ratio is more bigger. So which means, this tau, the DC offset is disappeared, it needed more time than this one, the B, right? Because B is smaller. So that's why we need to consider here this part. The peak point is different. So we, I already explained about the electromagnetism lecture about mechanical strength, which is magnetic force is induced like unintentionally, in negative way. We don't wanna, but it happened because of the negative way it happened. So we will say this is a mechanical strength. If you don't understand what I'm saying now, go to that lecture, okay? Electromagnetism part. So what I mean is the force is equal to proportional. So I current is to 2. You know what I mean? But this Ri is not RMS value, not RMS. This is instantaneous value, this peak point. That's why we really care about this, the Rx's ratio, because we don't want to get the damage on our electrical system, right? So that's why we need to reduce the fault current, right? So one example is we, adjust the Rx ratio. So let's move on. I'll explain more about it. Oh, yeah. So look at that. Here is, for example, I will get this source from the internet. So I will, attach this where I get it, this information. Okay. So look at that. There's two circuits, right? A, B. But what I meant is the jet is the same. Jet, the magnitude, you know what I mean? It's the same. But only differences is the ratio. One is 50, another one is 5. But look at that here. You can see this DC opposite. The A point is it disappeared, kind of a more long time, right? Instead, this B circuit, Rx ratio is smaller, right? So it disappeared. Compared to this two, circuit, it disappeared kind of sharply, right? Kind of fast. And what I said is we also need to consider, because of the magnetic forces happened, in negative way. So it break up the electrical system. So what I mean is that the magnetic force is, proportional to I is to 2. But this is instantaneous value, right? Which means peak value, this value. But you can see here, Rx ratio is lower. It's 388 ampere. Peak value is, but if the ratio is higher, the peak value is 485 amperes, which is really big differences. You know what I mean? Because we 222, I 222. You know what I mean? That's why I'm saying so. So this DC opposite is tau R X, or it gotta be R L. Same, I said, right? That's why this is really important, because of the peak values, and it makes more, I explained, Rx the ratio is more bigger. The I said the result is more asymmetric waveforms happened compared to here. What happened? Till here, almost, yeah, till here, asymmetric waveforms happened, but instead here, RX ratio is lower. Only short part, right? So yeah, that's I explained. And yeah. So conclusion is later you guys read it, okay? The RX ratio of circuit would dictate the magnitude of a DC component. I said, right? And the higher the RX ratio, the higher the circuit current is. You know what I mean? We explained about this, right? So yeah, later you guys read about this, and yeah, quick review is RX, values. It's affected the fault current, ratio. You know what I mean? The magnitude. So RX ratio is a more bigger. It makes a more asymmetric waveforms make it. And we consider about the peak values because of the magnetic force, Yeah, today's lecture is done today. Thank you guys.